Good afternoon, everyone. What we're going to do now is we're going to go for our 9th asynchronous lecture, and we are going to start discussing open quantum systems for real, now beyond the preamble, which we have already seen. And this is going to include master equations, which are very important when dealing with a variety of systems whose dynamics you're not quite sure about, but you need to model. So I hope you enjoy and see you soon. So the key issue that we're going to worry about here is how we want to describe the evolution of a system interacting with a very large environment. And we have some possibilities here. The first thing that we could do, for instance, is to write the time-dependent Schrödinger equation for everything, because the system and the environment, they constitute a closed system. And we know that closed systems are going to evolve unitarily under the time-dependent Schrödinger equation. So, okay, so we want to describe everything, so we make a bigger system. And we write the time-dependent Schrödinger equation for this bigger system, which includes the system we are interested in and the environment. In principle, it should work. In practice, you may stumble upon quite a few difficulties because the environment must include everything that is influencing or potentially may influence the system of interest. So if you are dealing, let's say, with a huge molecule with many degrees of freedom, or if you are dealing with a nanostructure and you don't really know what you need to include and how you would treat this theoretically, this can be a huge problem. Or you can try to derive an evolution equation for the reduced state whole of the system alone. And that's what we're going to see. Many times this is phenomenological. Many times it's a bit of a shot in the dark and you're making educated guesses. But this is a powerful formalism because sometimes you have no choice and you really need to go for what you can do. And that's why we spent a long time looking at density matrices and also reduced density matrices so that we would be able to do this kind of thing. So our goal is to find something similar to the Schrödinger equation. And here on the left-hand side, we have the evolution of the density operator, the function of t, the time derivative, is equal to a superoperator applied to this density operator, which is a bit like what you have if you compare it to the time-dependent Schrödinger equation, because we know you have a state vector in state space. You compute this time evolution, and what you do is you apply an operator to this guy, to this state space vector, and this operator then is minus I divided by h bar multiplied by the Hamiltonian. So effectively, that's what you're doing. And what we would really like to do is to find something similar, but considering our density operator, whereby this very likely is going to be a reduced density operator, because many times we don't know what our system is going to be. So let's start from the beginning and let's start writing rho dot t, whereby this is the time derivative. And we know the definition of derivative, right? We know that this is the limit of rho t plus delta t minus rho t over delta t when delta t goes to 0. So let's write that and let's analyze it in detail. And a consequence of this, and something that we can actually see, is that rho t plus delta t is depending on the density operator at a time immediately before. which is rho t. Why? Because we can see that on the left-hand side, we have this rho t plus delta t. On the right-hand side, we have rho t. Here we have the derivative with regard to t multiplied by delta t. So they are connected, and here the emphasis should be immediately before, because they are really separated by this infinitesimal amount of time, delta t. And if we look at that, just from this equation, the system's evolution cannot depend on, first, the state of the environment. We don't know the state of the environment. We're just saying that we have a density matrix of a particular system, not including the environment. And we are relating this density matrix at a time t plus delta t with a time t. So if the environment is changing this, how would you take this into consideration? First question. Second question, you are not taking into account the history of the system, because you just connect t with t plus delta t. So how about a situation in which you potentially could have an evolution of rho, of the density operator prior to t, so for some earlier time t dash, and this evolution would influence your dynamics? This could be a problem, but the way this equation is stated, which is something we have derived and stipulated here, we have something that we call Markovian evolution. And this means that the way a system will change will depend only on its states now, not in something that is happening before that, and not on something that is maybe being influenced by an environment. The environment is not playing a role, and the previous configurations of the system are not playing a role either. So this is what we call Markovian evolution. And in fact, this is named after Andrei Andreevich Markov, who made huge contributions to stochastic systems. And you don't find Markovian evolution only in quantum systems. You can find this also in classical systems. For instance, the weather is a case of non-Markovian evolution, because the weather, or if it's going to rain today or tomorrow, is going to depend on previous weather configurations, not only on what is happening immediately before, but on the day before, and maybe the day before the day before. It's difficult to predict, unbelievably difficult, but it depends on this configuration. So this is non-Markovian. But there is this game, snakes and ladders, in which the probability that you land on a ladder or on a snake is going to depend only on your current position. So I've never played it. I read that this is an ancient Indian game. In fact, this is a picture of a board associated with snakes and ladders from the Delhi National Museum. But the situation that we're going to have is that whatever you do in this game, you are reset. So your configuration is going to be reset. So whatever you do at the time t is going to influence what happens subsequently, but not what happened before that. So you can go back to square one. That's why people say when you're going through a tough time in life, you can, it's like going through snakes and ladders, because you're brought back to square one, or you are brought back to your current position. And by the way, I'm not afraid of snakes. In fact, I find them very cute. Since we're all a bit stressed with the lockdown, I decided to bring this picture. That's Jan, by the way. Really friendly guy. So I wouldn't be afraid. Depends on the snake, of course, if you land on a snake. But what matters to us is really that in a system undergoing Markovian evolution, whether the system is classical or whether the system is quantum, whatever happens has to depend on what happens immediately before. Not long ago, and there are no more intricate connections. It has really to be a connection between what we have seen, t and t plus delta t. And This evolution of a Markovian system is going to depend only on its reduced state, not on the environment. This means that the environment is not going to be influencing this state. So there's not going to be some kind of back reaction from the environment to the state. Otherwise, the evolution is not Markovian. And if you want to think about it in terms of information, this means that it's going to flow only from the system to the environment, only in one direction. So it's a one-way street, but not the other way around. So the system is influencing the environment or is providing information to the environment, but the environment is not sending something back. And we need to say this, that the evolution of most interacting quantum systems is not Markovian, because it's much more complex than that. But having said that, this can be a very good approximation to a lot of situations that you consider that a system has Markovian evolution. There are a few ones and a few models involving Markovian evolution, for instance, spontaneous emission, which is something that we are going to discuss, or sometimes a random walk, DNA models, many problems in statistical mechanics and also in thermodynamics are influenced by Markovian dynamics, Markovian evolution. And what we're going to do then is we're going to have a look at Master's equations, because this equation that we wrote and that we were analyzing and we're saying, okay, this equation shows me that the derivative has to behave in a certain way, and rho t can only depend on rho from a immediately previous t, or rho t plus delta t can only depend on rho t. And on the right-hand side, we have some kind of super operator, which, if you remember, is an operator that modifies another operator. So this is Markovian evolution. This is what we can describe. Now we're going to make some assumptions about this super operator. And this is what we call also Master equation. So this is an equation which is describing an evolution of a system in a Markovian fashion, in a Markovian manner. So this is a super operator, and this is the density operator of the reduced system that would be the system we're trying to analyze. So how can we derive this equation? We need some explicit form of this equation. And this is something that we would like to establish, and we don't know how we are going to derive that. So this is a question that we'll ask ourselves. And there is one possibility. For instance, we can write down Hamiltonian for the full system and environment. Then we can manipulate the expression, perform a partial trace over the environment, and then we can derive an equation, which would be the most rigorous way of doing this, because you can say, okay, I consider the system plus environment a closed system, and then I trace out the degrees of freedom which are associated with the environment. However, it can be that you don't manage to do that. So this, I mean, is a key advantage. This would be a really, really rigorous way of doing that. But the drawback would be that you may have hugely cumbersome derivations. Don't forget that these systems, they are normally complicated, and they are not normally extended systems with very intricate dynamics. And whatever you derive is going to depend on the specific Hamiltonian that you used as your starting point. So this is another drawback, which is this would be Hamiltonian specific. Another possibility is we're going to derive a general form in which all Markovian master equations can be expressed. And we are going to understand this equation phenomenologically. So we're going to tweak things in a way that it is going to agree with your experiment, it's going to agree with what you observe in your system. You're going to bring some kind of intuition there. It's not very rigorous, but this can be powerful when you can make very good educated guesses to describe a particular physical system. And what we mean here with phenomenological is that if we observe some event, we can associate operators in the master equations with the events that we observed. If we observe certain thing is happening, then we can invent an operator which is going to describe that in a satisfactory way. And this is not, as I said, totally rigorous, but sometimes even you have no choice because the system is so complex, you don't know what is happening. And our starting point is going to be this equation, which we had obtained from the evolution of the density operator ρ. So here we're connecting ρ at a time t plus delta t with a time t. You here have the derivative plus this delta t, and this is exact if you take the limit of delta t going to 0, which is actually how you define your derivative in the first place. And what we would like to do is to derive an approximation for ρ, which is accurate in first order of in delta t. So this is a tough job, but that's what we're going to try to do. And we're going to start always when you derive something, even if it's something phenomenological, you have to start from a set of assumptions that are really clear cut in your mind, and you know how you're going to approach the problem. So first, you assume that the evolution is Markovian, so that this is valid in the first place. You assume that there is a superoperator transforming ρ t to ρ plus t plus delta t. And this third one is a tough one, but in many, many cases this holds. Remember from what we have seen in the previous lecture that many times we can write superoperators in the cross operator sum representation form. So they have to satisfy a few properties. So we have discussed them, that trace has to be preserved. This has to be completely positive, and hermeticity has also to be preserved. If this is fine, if these three properties hold, then you can go for it. And that's what we're going to have a look next. So next, we're going to have a whiteboard derivation in which we are going to see, based on these assumptions, how we can derive Markovian master equation using superoperators. Okay, so see you soon.